Okay, so welcome back to another video. So in today's video we actually got a infinite series that we'll be evaluating. So the infinite series of the Riemann-Zeta of 2n plus 1 divided by 4 to the power n multiplied by 2n plus 1. Ooh, that sounds a bit complicated right there. But no worries. We're actually going to use a couple functions to help evaluate this series. And not only that, we're actually going to use we're actually going to do some integration to help manipulate things a little bit with this series as well. So with that, let's actually start off by using the series expansion of the digamma function. So let's see, series expansion of the digamma function. And if you're wondering, the digamma function is actually just the logarithmic derivative of the gamma function. So first, let me first define two functions and a series representation. First, we have the following. Okay, so the first digamma function, psi of x plus 1 is equal to the following expansion: negative gamma, lowercase gamma, which is the Euler-Mascheroni constant, plus the infinite series of x to the power n multiplied by -1 quantity to the power n plus 1 multiplied by the Riemann-Zeta of n plus 1. And I expanded this out, so you get that it's negative gamma, and then the series starts from here. Riemann-Zeta 2 times x minus Riemann-Zeta 3 of x squared plus Riemann-Zeta 4x cubed, and then so on and so forth. Okay, and now let's define the second digamma function. Okay, now the second digamma function, psi of 1 minus x, is equal to the negative lowercase gamma plus the infinite series of, this time, negative x quantity to the power n multiplied by -1 quantity n to the power n plus 1 multiplied by the Riemann-Zeta of n plus 1. I expanded this out. It's very similar to this, except all the terms from this series expansion here, they're all negatives, while you have over here that starting with positive Riemann-Zeta 2 of x, it alternates its signs with every other term. So this is for n is equal to 1, positive, n is equal to negative, n is equal to 3, positive, n equals 4, negative, so on and so forth. They alternate from there. So now that we have these two digamma functions, let's actually add these two together. So you can actually see that I can do this like a systems of equations in a sense. So how about we add these two equations together, like so. Okay, so added these two functions together, and you start to see that this is the expansion when you add these two expansions together. So negative gamma minus plus negative gamma, -2 gamma, and you'll start to see that gamma 2x minus gamma 2x, they cancel. So it's like every other term cancels except for the n equals 2 index, and then every other number. Basically, the even indexes, it's a double quantity, while the odd indexes, the terms cancel each other out. Okay, so we got this series expansion. Therefore, I can actually rewrite this in a form of an infinite series. Specifically, this is -2 gamma minus 2 times the infinite series of let's see, it's Riemann-Zeta of 2n plus 1, then multiplied by it's just under 1, it's not under a fraction. So this is, let's see, 2n plus 1, and then multiplied by x to the power 2 times n. Okay, so far so good. So let me just underline what we have so far. So, okay, -2 gamma minus 2 times the infinite series Riemann 2n plus 1 multiplied by x to n. So you might be thinking to yourself, like, how do we move on from here? So how do we continue to evaluate this? Well, let's actually consider the following, and I'm going to write this in orange. How about instead we actually take the integral of this expression over here, and how about we integrate this from our bounds between let's see, so we have the integral. How about we evaluate this from 0 to t? Okay, and then let's see, we write the same thing, 2 gamma minus 2, then the infinite series of Riemann-Zeta of 2n plus 1, then x to the power 2n dx. Okay, and that's not that hard to show. You can see that this is just, let's see, it's just negative 2 times x multiplied by gamma, and then minus, so okay, that depends on x, so let's see, we can just use the power rule here. So let's see, it's x 2n plus 1, then divide by that. So it's, let's see, minus 2, then infinite series n is equal to 1 of Riemann-Zeta 2n plus 1, then x to the power 2n plus 1, divide that by 2n plus 1. And then we can just evaluate this from our bounds from 0 to t, and that's not hard to show, which this is just negative 2t multiplied by alpha, and then minus 2, the infinite series, let's see, Riemann-Zeta 2n plus 1, then t to the power 2n plus 1, divided by 2n plus 1, and I can actually simplify this out a little bit, so let's see, negative 2t gamma, and then minus 2. Now notice that we have 2 to the power 2n plus 1, but this can be rewritten with using our rules of the base. So this is just 2 to the power 2n multiplied by t, but we can actually move this outside of our series since our series depends on the terms of n. So it's multiply 2 times t, and then our infinite series again. So like so, plus 1, and then t to the power 2n divided by 2n plus 1. Okay, good. So we actually evaluate this. So what this means is we actually not only took the integral of our series expansion over here, but really we're actually taking the integral of the sum of our digamma functions. So let's actually rewrite that as well. So it's from 0 to t of our digamma functions, or the sum of our digamma functions, x plus 1, and plus psi of 1 minus x dx, and that's equal to this following over here, negative 2t multiplied by gamma, okay, and then minus 2 times t, then multiplied by the infinite series, n is equal to 1 of 2n plus 1, then t to the power 2n divided by 2n plus 1. Okay, good. So we have this, and now let's actually do something here. That way we are getting closer to achieving what we're trying to solve, our series in particular. How about now next? Well, first let me just underline this in black to see what we established now. Okay, so now like I said, let's figure out a way on how to achieve this. How about instead, since we have our integral from 0 to t, how about this time we plug in our parameter? So let's say we plug t is equal to 1/2. Okay, so when we do this, we plug t equals 1/2 like so. Okay, so plug t equals 1/2, then we just plug t equals 1/2 for over here. So let's see, I'll just plug in negative 2 multiplied by 1/2 gamma, then minus 2, plug in 1/2, and then our infinite series, let's see, Riemann-Zeta 2n plus 1, then 1/2 to the power 2n plus 1, like so. Okay, good. So when we plug all this in, we get that this is just negative gamma, so this is minus 1, and then let's see, infinite series n is equal to 1 of Riemann-Zeta of 2n plus 1. As you can see, 1/2 to the power 2n is just 1 divided by 2 to the power 2n. Really though, that could actually be, that goes under the denominator. So it's 2 to the power 2n, and then multiplied by 2n plus 1. I can also simplify this a little bit. Specifically, we have that 2 to the power 2n. Using our rules of exponents, I can actually just factor out the n from the exponents, and therefore we just get 2 squared, which is just 4. So the base is 4, rather. So this is just 4 in the denominator with the power n, and then multiplied by 2n plus 1. Okay, so notice that this quantity, this term here is exactly what we're trying to achieve so far, but we're actually not done there just yet. Okay, so far we already simplified out the right-hand expression over here, but now all that's left we need to do is we actually need to evaluate, or rather simplify, the left-hand side. So how do we do that exactly? Well, remember what I said by the definition of the digamma function is the logarithmic derivative of the gamma function? Right, so we're actually going to use that property to help evaluate this integral on the left side. So I'll note that, or rather I'll say that recall for the digamma function that, let's see, for standard psi of x is simply just equal to, simply just equal to the derivative, so d over dx of the natural log of gamma x, like so. Okay, good. So I'm just going to use this little fact to help establish this. So what this means is, actually, another thing I want to note, or rather, I'll actually save that for later. So first, let's actually evaluate this left-hand side first. Okay, I expanded this. I just rewrote the left side expression, and then rewrite this in terms of just using our fact with the derivative of the natural log of the gamma function. I also just rewrote, let's see, 1 minus x. I just rewrote this as negative x plus 1, just using the standard formation of how gamma functions are usually defined. Usually just the variable comes first and then your constant. So I just wrote it in this sense. Still means the same thing as this. Okay, so anyway, when I take the integral of both sides, simply you just use the, this is just a fundamental theorem of calculus, so you take the integral of its derivative, you just cancel that each other's out, and you just get that this is just the same function. So it's just the natural log of capital gamma of x plus 1, okay, and then plus the natural log of, or rather, this is actually supposed to be negative, just simply because there's a negative x over here when you do that substitution. So that's a minus over here. Apologies. Now the other facts that I want to mention using of gamma functions. So note that, and you can simply just compute this yourself and evaluate this just to verify it if you want to. But note that gamma of 1 is just equal to 1, and gamma of n plus 1 is equal to n multiplied by gamma of n. So it's just those two facts that we're going to be using of the gamma functions to help evaluate this, our evaluated integral. Okay, now when I evaluate our bounds, let's see, we get that this is, first I'll start off with our 1/2. So this is the natural log of gamma of 1/2 plus 1, which is just 3 over 2. I'll just write this in decimal, 1.5. And then subtract that with the natural log of the gamma of 1/2, well, let's see, negative 1/2 plus 1, which is just 1/2, 0.5, I'll write that. Okay, and then subtract this with the evaluated terms at 0. So let's see, 0, so this is gamma of 1, and then minus the natural log of gamma, and let's see, 0, and that's also 1 as well. You can see that natural log of gamma 1 minus natural log of gamma 1 is just 0, but you can also check to see that I stated that gamma 1 is equal to 1. When you substitute this back in, you just get that this is 0, and then that's 0, so 0 minus 0 is 0, so that cancels out. So therefore, we're left with just the left side of the terms that was evaluated at 1/2. So the natural log of gamma of 1.5 minus the natural log of gamma 0.5, but I can actually use our rules of natural log to convert this into just one natural log, which is simply just gamma of 1.5 divided by gamma of 0.5. Okay, And then we're going to use the rule, our little fact that gamma of n plus 1 equals n times gamma n, and then rewrite this numerator from inside the natural log. So you can see that 1.5, so let's see, so minus 1. So we can get that n is equal to 0.5. So we get 0.5 multiplied by gamma of 0.5, and then divided by gamma of 0.5. And you start to see that the gamma functions above 0.5 cancel each other out. So we get that this is just the natural log of 0.5, where you see that this is the same as the natural log of 1/2. Using our rules of natural logs, you see that this is the same as 2 to the negative 1. Move that exponent -1 to the front of the constant, so you get that this is just the negative natural log of 2. Now let's reiterate some things, okay? So far, we have this integral. The integral from 0 to 1/2 of our sum of the digamma functions, x plus 1 and then 1 minus x respectively, is equal to the right hand side, which is negative gamma minus the infinite sum of Riemann-Zeta 2n plus 1 and then divided by 4 to the power n multiplied by 2n plus 1, which is specifically what we're trying to solve from here. But that's just the right hand side. We showed the left hand side, which is this integral, is equal to negative natural log of 2. So this means if we set the two sides equal to each other, so I'll put it this way. Okay, I just rewrote the what we're given, or what we were trying to solve from earlier. This integral, we showed that this is equal to negative ln of 2, but we also showed that its extreme right hand side is equal to negative gamma minus the infinite series of that given. And now we're pretty much just done. We got one more step to do. Basically just do the algebra. You just add gamma to both sides and then just divide -1 to both sides of the equation to get the given our given series as the final answer. So therefore, just skipping steps like I just said. So therefore, our infinite series, the Riemann-Zeta of 2n plus 1 divided by 4 to the power n of 2n plus 1, this is simply just equal to the natural log of 2 minus gamma, where gamma is the Euler-Mascheroni constant. And there you have it. Underlined in this, or rather in this big box, drawn in this big box. Alright then, so that's pretty cool if you ask me.